We'll look now at some artifacts that relate to the Doppler controls. Here, we're looking at an artifact called wall thump. It's caused when motion of the walls causes Doppler signals that are not sufficiently well filtered out by the wall filter. In this particular case, I've artificially induced it by reducing the wall filter below the setting that the machine had chosen. So we have an inappropriate wall filter setting, and the result is that we are detecting moving walls. You'll notice that the way this appears on the spectral display is bright white blips along the baseline, which should have been filtered out, but they're breaking through the filter. And you'll notice that they line up with the beginning and end of each systole. This is easy to understand since it's at the start of systole and then the end of systole that the vessel is expanding and then contracting at its maximum speed. So that's when the walls are moving most dynamically. This problem is easily fixed, of course, by increasing the wall filter to an appropriate setting. It's perfectly possible to have the wall filter set too high as well. In this case, we're looking at an umbilical artery signal. One of the most important measurements when you're looking at a compromised fetus is the end diastolic velocity. We can't see that here because the wall filter has been set too high. Once again, this is easily fixed. Now we'll look at the issue of sample volume size. Here we have a standard acquisition with normal settings, a relatively small sample volume placed in the center of the vessel. The spectral tracing, as usual, has a significant window, in other words, an echo-free area underneath the spectral tracing. This is because we're only seeing the higher velocities around the center of the vessel. Here, I've artificially increased the sample volume size so that it spans the entire vessel. Now we're seeing the full range of velocities, from the fast-moving blood in the center to the very slow-moving blood near the vessel walls. The result is the spectrum has filled in, and it looks very much like the pathological spectrum that you might get if you had turbulent or disturbed flow. So you should be careful to stick with standard sample volume size, because otherwise you may produce misleading results like this. Now let's have a look at the effective gain on the Doppler spectral display. Here the gain was set too low initially and then just steadily increased as the display swept across the screen. What you can see is that on the left, the signal is too dark. Moving to the center, we have an appropriate setting of the gain, and we can see the full height of the spectral tracing. Over on the right, the gain has been turned too high. The spectrum itself is now nearly white, and we're seeing a lot of background noise caused by electronic noise within the machine. So the gain is definitely too high at this point. So clearly there is an appropriate middle setting or range of settings where the gain is neither too low nor too high. Now let's look at the effective gain on color Doppler. Here the gain has been set too low. The machine is detecting faster velocities, but it's missing the slower moving blood and not displaying it. I mentioned before that one of the features of color Doppler is that it is relatively poor at detecting slower moving blood. What we need to do here, obviously, is to increase the gain. Here the gain has been increased to the point where it's optimized. The vessel is nicely filling with color, and there is no spillover, no significant spillover of the color into the tissue areas. This is what it looks like when the gain is too high. So now we do have significant spillover of color into what are obviously tissue areas. So the machine's ability to determine what is blood and what is tissue is breaking down because the gain for the Doppler is simply too high. Now I'd like to just talk about directional effects or Doppler angle effects. We're looking here at a curved probe, and we've produced a color image of a straight vessel. You'll see the colour varies continuously from one side to the other, and this is because of the angle effect. In the diagram, I'm highlighting the fact that with a curved probe, and the same would be true with a phased array as well, every beam has a different direction, and since this is a straight vessel, that means every single beam has a different Doppler angle, and that produces the variation in colour that we see in the image. Looking at the image, I have no way to tell whether the flow is uniform along the entire length of that vessel or whether it varies in some way. And that's because the angle effect completely masks whether or not there's any variation in velocity. So we've looked at just a few artifacts associated with controls. We looked at wall filtering, we looked at the sample volume size, and I should mention that if you position the sample volume wrongly, you'll obviously get different waveforms. For example, if the sample volume is not in the center of the vessel, but is to one side, then you won't see the peak velocities in the vessel. You will get incorrect measurements. I've looked at gain both in the context of the spectral tracing and color, and I've just highlighted the angle effect or the Doppler angle effect for color and cautioned you not to try to make inferences about velocity variations from looking at a color image.